Welcome. In this session, I will describe an alternate way of finding limits of rational functions at infinity and negative infinity. It's a little bit shorter than the method I described last time, and it's based on the observation that for a rational function, we can rewrite it, factoring it as some power of x, which is namely the power of x, which is the difference of powers of x in the numerator and denominator, times another factor in which each term can be written either as a constant or as reciprocal of a positive power of x times some constant, which means it's just the ratio of the highest degree terms that determines the limit of a rational function at infinity or negative infinity. So in particular, if we have a function, rational function in which the numerator and denominator have the same degree, like in this example, the limit will be a non-zero finite number given by ratio of the coefficients. So, in other words, I can find the limit by the following process. Take the highest degree term in the numerator. In our example, it's 3x squared. And in the denominator also, just keep the highest degree term, ignore the others. In this case, the highest degree term is negative 2x squared. This ratio is 3 over negative 2. And so that's the limit of the given rational function as well, because limit of a constant is itself. If the numerator has smaller degree, when you look at the ratio of the highest degree terms, in our next example, when we look at the ratio of highest degree terms, for example, I have 3x squared for the numerator. For the denominator, highest degree term is 2x cubed. The ratio is a constant times reciprocal of a positive power of x. So I get 3 over 2x. I can think of it as 3 over 2 times 1 over x. 3 over 2 is a constant, its limit is 3 over 2. 1 over x has limit 0. 3 over 2 times 0 is 0. So the limit is 0. Now we come to the case where numerator has larger degree. So in our example, the numerator has degree 3, denominator has degree 2. The corresponding terms are 2x cubed for the numerator, negative 3x squared for the denominator. When I simplify this, I get 2x over negative 3, which I can think of as 2/3 times negative x. Now 2/3 is a constant, it's a positive constant. We're finding the limit as x goes to negative infinity, which means that negative x goes to infinity, positive infinity. So I get 2/3 times positive infinity, which is also infinity. So the limit of the original function is also infinity. So we can always use this process for rational functions in standard form. But you have to be careful if the function is not in standard form. This doesn't quite work. In the next example, if you try to do this term by term, using the method I just described, you will end up with infinity minus infinity. This is one of the prohibited cases for the limit laws. The limit theorems don't work when you have infinity minus infinity. We can get around this by rewriting the expression as a rational function in standard form. In other words, we want to combine the two fractions into a single fraction by using a common denominator. The least common denominator will be 2 times 6x plus 5, and I rewrite each fraction having that as a denominator. So in the first fraction, I need to multiply the numerator also by 6x plus 5. In the second, I need an extra factor of 2. Now I'm going to combine the two fractions. Since they have the same denominator, I just do the subtraction in the numerator. Before I do that, I need to distribute the x and the 2. And I should also distribute the minus. So in the end, I get 6x squared plus 5x minus 6x squared plus 10x minus 14. I can combine the x squared terms. 6x squared minus 6x squared is 0. And I can also combine the x terms. 5x plus 10x is 15x. So I get 15x minus 14 over 12x plus 10. This is the same rational function as before, but written in standard form. Now I can use my shortcut method to find its limit at infinity. So you just take the highest degree term in the numerator and the highest degree term in the denominator. These are 15x and 12x respectively. And I take its limit as x goes to infinity. And that's 15 over 12 or 5 over 4. So that will be the limit of the original function as well. This concludes the description of this alternate method, and I will stop this session here. Goodbye for now.